Hello, calculus fans. Today we will look at the first part of section 8.3, which deals with hydrostatic pressure and force. Section 8.3 is a pretty huge section, so I cover it in two parts. The second part deals with center of mass, so we'll cover that next time. So if you've ever been scuba diving, you'll realize that water pressure increases as you dive deeper. It's because the weight of the water above you will increase. I'll tell you one other thing about scuba diving that I know from my vast experience of scuba diving once ever in my life. When you are scuba diving for the first time, I noticed that every fish looks just like a shark. That's what I noticed. A little bit terrifying. And then it gets closer and it's like, oh, it looks actually like a bluegill. But they do seem to look like sharks at first. At least for me, when I don't really know what I'm doing. But in this case here, we've got a couple scuba divers, and they're at different depths. So the force on this person's head is basically the weight of the water in the column above. So there's a smaller column here. So this would result in, let's say we'll call this force 1, which is like this. The force 2 is going to be a bigger force because there's more weight above this person's head. So basically in this case we would say, since force 2 is greater than force 1 because of the weight of the water in the column above. Force, as we know, because we studied this in chapter 6 and 6.4 when we're dealing with work problems, force is measured in pounds if we're using the U.S. customary system, or in newtons if we're using the metric system. So those of you who liked section 6.4, you're probably going to like this part of section 8.3. A lot of the concepts are the same, and even the way we approach the problem will be similar. So Stewart in the textbook uses a little bit different approach in some of the problems, but I'm going to use a very consistent approach throughout, so what we do here will be familiar to what we did in section 6.4. All right, so we start off, we've got some terms we need to be clear on. So pressure is force per unit area. So in other words, we could say pressure equals force over area. It's force per unit area. And then we're going to, just along the side here, I'm going to develop some formulas that we need. Okay, so we'll start with that one. We'll start, number one, let's say we'll start off with pressure equals force per unit area. And first we're going to be dealing with weights a lot. So we'll use force equals mass times acceleration due to gravity over area, right? And we talked about that before. So from Newton's second law, we have force equals mass times acceleration, and we're just going to use g, which is the acceleration due to gravity, and that'll give us our weight. Second thing, we need to revisit density, usually abbreviated with the Greek letter rho, and this is mass density. This is mass per unit volume, or mass over volume. Well, this implies if we were to solve this equation for mass, so we multiply both sides by v, then we get mass equals density times volume. And for volume, think of if you have a volume of a cylinder, so you got a circle on the bottom, it comes up. So volume of a cylinder is just the area of the bottom times the height, right? Volume of a cylinder is basically pi r squared h. Or even if you have a box, the volume of a box is the area of the bottom of the box times the height. So we're going to think of that here. So we're going to just write volume is area times height, right? So we'll have the mass equals rho times area times height. And then we're going to just change this a little bit. So this h is height. Since we're going to be talking about things underwater, we're going to write it like this. We're going to say mass equals rho times area times depth. Okay, same sort of thing, but we're going to use this formula so we can get the depth of the water involved. Okay, so third thing we need, we're going to go back to pressure equals force per unit area. And then force is mass times gravity per unit area. And then we're going to use this mass up here, use this definition or this formula for mass. We'll say that is going to be rho times A times D times G all over A. So we're just swapping out, we're keeping the G here, but the M we're putting in this with this formula. Then we can cancel these A's. The areas cancel. So that will give us pressure equals rho. And I'm going to write it like this and move the G here and then D. So we've got mass density, right? Rho is mass density. We're going to multiply by G, the acceleration due to gravity. And we learned before that when you take a mass and multiply by the acceleration due to gravity, you get the weight, right? So we're going to, if mass density times acceleration of gravity gives us the weight density. And the Stewart textbook uses delta for that. So we have this, delta is weight density, which we talked about before. So that means we started with pressure. So a pressure equals weight density times depth. We're going to use that formula, so let's put that up here. So pressure equals weight density times depth. We'll be using that a lot in this section. Okay, and finally we've got, we'll start with pressure equals force per unit area again. And this time we're just going to solve this for force. So multiply each side by A, and you get force equals pressure times area, and that is the third and final box here. That's what we used to fill that in. Alright, so that gives us what we need. We're going to be using these three formulas quite a bit in this section. Then there's a list here of various weight densities, and these are in pounds per cubic foot. Remember, the other way to measure this with a metric system would be newtons per cubic meter. So we've got some, let's see, gasoline, I don't know. I'm not sure how this one got in there. That was definitely a mistake. Let's see, you got some water. We'll use water quite a bit. Molasses. You ever hear the expression slow as molasses? Turns out molasses is not as slow as it seems. There was the Great Molasses Flood of 1919 in Boston, where 2.3 million gallons of molasses was up in a storage container, and the storage container broke, and it released 13,000 tons of molasses. And basically, from the reports, it moved at about 35 miles per hour. It was a huge wall of molasses coming down in the middle of the city, and it just would be like this blob that just absorbed whatever was in its path. So it ended up killing 21 people, but it like ran into over 100 people. There were horses, just a giant mess. But it's got a pretty high weight density. And then there's mercury, which is really crazy. There used to be mercury in thermometers. It's got a high coefficient of expansion. It doesn't stick to glass. Up until the 2000s, there was mercury in thermostats in houses. Those have been replaced now by digital thermostats. But if you've ever seen mercury, it's really weird. It looks like a ball of metal that rolls around. I swear we used to play with this in school. I swear they used to let us play with it, because I can remember having it roll around in my hand. We were kind of passing around in the classroom, and that is definitely frowned upon now. It's a hazardous material. So it's not even used in thermometers anymore. Now it's been replaced with alcohol. And it's really a strange substance. It melts at 38 degrees below zero in Fahrenheit. So it's basically, whenever you see it, it's in its melted form. But it's got some good properties for electronics. But again, it's hazardous, so it's not used anymore. But look at the or the weight density on that. It's just crazy. Here's a quick application of the uses of pressures and forces. So imagine we have a dam. This is a dam here. And dams typically get a lot wider at the bottom than at the top. So this is all water. This is a dammed lake. And then down here is the river. So you got this water here. And there's just a lot of pressure. And the farther down you go, the more pressure there is. So there's tons of pressure. And they'll have this little gate down here, sometimes called a sluice gate or a penstock gate, but this is under tremendous pressure. So engineers have to be able to figure out how to open that gate and close it under the pressure, and water will come spilling into here. And then to make a hydroelectric dam, they'll have these turbines in here, and the water goes through here. So as an example, in the Hoover Dam, the water goes through here at about 85 miles an hour, which is brings a lot of pressure here on these fan blades, which will spin to generate electricity, and then it just shoots out here. So there was actually a problem there because there was such a drought for so long that the engineers were afraid that this wouldn't work. The pressures, Lake Mead was drying up so much that there just wasn't the pressure here like there used to be. You may have even seen on Mythbusters one time, they had a car that was underwater. I think it was in a swimming pool, and it wasn't really very far underwater at all. And it took just crazy amounts of force to open the door. Yeah, I think they said it was under like 2 feet of water, and it took 350 pounds of force to open that door under just 2 feet of water. So it's not hard to imagine the crazy amount of pressure over here at the bottom of this dammed lake where you're trying to open and close these gates here. But it works out well for generating electricity. Of course, if you are the engineer making the big bucks designing these gates, you're going to have to know all about pressures and forces. So speaking of that, let's fill in these blanks here. A little reminder. So pressure is force per unit area, which implies that force is pressure times area, and pressure is also weight density times depth. All right, so let's talk about units of measure. As usual, we'll have our two systems, the U.S. customary system that we insist on using, and then also the metric system. So units of measure, let's start off with pressure. Units of measure for pressure, well, all right, pressure equals weight density times depth. So weight density in the U.S. system is pounds per cubic foot, and depth would be, of course, in feet, which means feet would cancel. It would take one of those, which would give us pounds per square foot. Now, we normally convert this to pounds per square inch, which is known as PSI, right? Pounds per square inch. Now, if you're using the metric system, and you have pressure equals weight density times depth, well then weight density is in newtons per cubic meter, and you times by depth, which would be in meters. We once again will get these units to cancel. This will be meters squared. So then you have newtons per square meter. And what this is typically called is a Pascal, abbreviated PA. And by definition, 1 Pascal equals 1 Newton per square meter. And there are actually quite a few different units of measure for pressure, but we'll typically use pascals and either pounds per square foot or pounds per square inch. All right, so that was pressure. So let's look at force, which we're familiar with this, right? We're familiar with this from before, from chapter 6. So force equals pressure times area. So as far as the units of measure are concerned, pressure, if you're using the U.S. system, if we start with pounds per square foot, and area is going to be in square feet, right? So that just means that these would cancel, and we get pounds, which we already knew that. We measured force in pounds when you're working on those work problems. And then, of course, in the metric system, you'd have pressure being newtons per square meter. Area is square meters, so you cancel there, and you end up with newtons. Okay, so this is the units for pressure and force, and there's just a couple other things we need to know about this. So there's an important principle in fluid pressure, and it's the fact that at any point in a liquid, the pressure is the same in all directions. So if you are underwater at some point, at this point here, the pressure in all directions is the same. Okay, so we need to know that. Also, fluid pressure is proportional to depth. And we know that because we have pressure equals weight density times depth. And if you look at this formula, you can see that only the depth matters. The only way you're measuring pressure, because this will be some constant, just the depth, right? So it's proportional to depth, which means that the size and the shape of the container, those don't matter. So the pressure at the depth of 4 feet is the same whether you're in a small tube of water, a swimming pool, Reed's Lake, or Lake Michigan. As long as the weight density is the same, the only thing that matters is the depth. All right, and now we are ready to actually see the kinds of questions we're going to run into in here and see if we can come up with a plan of attack that will work on these problems. Example 1 says we have an isosceles triangular plate. Okay, isosceles. What does that mean? 2 equal sides, right? 2 equal sides. So therefore 2 equal angles. But we've got this triangular plate with vertex down, so the point is down. It is submerged vertically 1 meter below the surface of the water. So the base of the triangle is 4 meters and the height is 4 meters. Find the fluid force against one face of the plate. All right, so here's the method we're going to use. We'll draw a picture, and then we're going to consider a little sample strip, that's on this triangular plate. We're going to figure out the force against that little sample strip, and then we're going to integrate to sum all the sample strips. So let's start off with a picture, and I'm going to do the same thing that we did in Chapter 6. I'm going to use the XY plane and try to put it there, typically centered, in a way where we can, if we need to come up with equations of lines, we can do that pretty easily. So this is what I've got here. This is the water level. The base of the triangle is 4 meters, so this is the base is 4 meters. The height is 4 meters, so this comes out to 2. Goes back to -2. So we've got this here. This is all water here, and so this is under the water. We want to find the force, the fluid force against one face of the plate. All right, so what we're going to do is just consider a little sample strip here. Consider like a little rectangular strip. And what we're going to do is find the fluid force against this sample strip. Also, I probably should have mentioned the title of this section is hydrostatic pressure and force. So hydrostatic, hydro meaning liquid, static meaning at rest. So the liquid's at rest, so it's just sitting there. Okay, so we're going to find the fluid force against this little strip, and then we'll integrate to find the force against all these strips on this plate. So the first thing we want to do is find the area of the strip. So area of the sample strip. Well, the area of this thing, if I know this point here, if I know this x coordinate, then this distance is x, and because of symmetry, this will be 2x. So since it's a rectangle, the area is length times width, so the length is going to be 2x. And what do you think we'll call for this little height here? It's like a change in y, right? So we could call it dy. Okay, so we could say that the area equals 2x dy. And when these are placed symmetrically like this, they won't always be, but when they are, a lot of times the area is just going to be 2x dy, right? Because if we know that x coordinate on this line, if we know that x coordinate, we can double it, and that will give us the length of the rectangle. and the height is just going to be dy. Okay, so we've got the area. Now we need to find the pressure against the strip. So let's say pressure against our sample strip. Well, pressure equals weight density times depth. We use this formula a lot. Pressure equals weight density times depth. Well, the weight density here, because we can see these, the measurements are in meters, so we're using the metric system. So the weight density of water in the metric system is 9,800 newtons per cubic meter. And just to review, just to make sure, so we talked about this in chapter 6, but let's just make sure. So weight density of water, weight density, delta, right, weight density is 9,800 newtons per cubic meter if you're using the metric system. And then for the English system, what we've been using is 62.5 pounds per cubic foot, right? So we're going to use those again, same as before. So when we're talking about weight density of water with the metric system, we're going to use 9,800. Weight density of water with the English system, we use 62.5. Okay, so continuing, we've got 9,800 and the depth. All right, so the depth here. All right, so this point right here, we were talking about this being x. Well, this here is just going to be y. So this distance is going to be 5 minus y, right? Because this water level is at 5 meters. So if this is y, this is going to be 5 minus y. So the depth here is going to be 5 minus y. But I'm going to tell you something that will always be true here. When you're working on these problems, the depth is always going to be the height of the water minus y. You can always use height minus y for the depth. So just look at the height, because the height would be dependent upon how you set this grid up, right? So if we set it up like this, which you don't have to, I could literally put this anywhere. It seems easy to me to do it this way, where the height is 5. But, you know, I could have set it up like underneath here. Could have put it down here, or however you want to. It really doesn't matter. But when you do this step here, weight density times depth, you can always just go height minus y. The height, the way this is set up, is 5. So 5 minus y. Okay, so that gives us the pressure. And then finally, we need the force against the sample strip. And force is just pressure times area. Pressure times area. We'll use this formula a lot. So we have the pressure and we have the area. So the force is just those two multiplied together. So that's going to be, I guess, 9,800 times 5 minus y times 2x dy. So that's the force against that sample strip. So then to find the total force, we just integrate. So I'm going to take this, I'm going to pull the constants out front. So we'll get 9,800 times 2 times x times 5 minus y dy. And what we're going to do here is we're going to integrate wherever these strips are. So the strips are going from 0 to 4. Right, so we integrate where the strips are. And then, can you see a problem we're going to have here? The problem is this is a dy problem and we've got an x. So we just need to deal with that x. So what we'll have to do is see if we can come up with maybe the equation of this line right here, which would be pretty easy because this line goes through the point 0, 0, right? It goes through right here at the origin. And then also right here, this point is the point 2, 4. So we just have to find an equation of a line through these 2 points. Well, we can see the y-intercept b is 0, right? So if we find the slope here, Let's see, the slope is going to be 4 minus 0 over 2 minus 0, right? y2 minus y1, x2 minus x1. So the slope is 2. And as I said, we can see right here that the y-intercept is 0, goes right through the origin. But if you don't notice that, you can still use the usual routine. We plug in a 2 here, and we pick the point 0, 0. Let 0, plug in 0 for x, 0 for y, and we'll get 0 equals b. So the equation of this line is y equals 2x, right? 2x plus 0. Now we need this to be x in terms of y, right? So to fix that, we just divide each side by 2. And what we'll finally get is x equals 1/2 y, right? Divide each side by 2. All right, so then for this x, we can put 1/2 y in its place. So when we plug in a 1/2 y here, that 1/2 will cancel with the 2. So what we'll end up with is 9800, 0 to 4, and then y times 5 minus y dy, which is 9800, 5y minus y squared dy from 0 to 4. So I guess this one's easy enough. We can just go ahead and integrate. So we'll get 9800. We just have the power rule twice, right? So this becomes y squared divided by 2, which gives us 5/2 y squared minus 1/3 y cubed from 0 to 4. And just to save you some time, if you plug in the 4 here, you can see plugging the 0 isn't going to do anything for us. So you plug in the 4, go through the calculations, and we will get something like 182, 933, and 1/3. And what are the units to measure here? Well, remember, ultimately this is force, right? It's force with a metric system, so that unit of measure is going to be in newtons. Let's take a look at example 2, where we talk about a truck hauling milk in a 6-foot diameter cylindrical tank. It's mounted horizontally on the bed of a truck. We want to figure out how much force does the milk exert on each end of the tank when the tank is half full. So you can see there's got this milk in here, half full. We want to figure out the force exerted on each side of this tank. So what I'm going to do is I'm going to orient this at the origin of the XY plane, right? So this is kind of what we've got. But what we need to do is come up with a way to get a handle on this thing. So we've got a 6-foot diameter tank. So if we go to basically put a circle here. So that this is 3, this is -3, this is +3. Of course, this is -3 over here also. And so there's a couple ways you can do it. You can orient it that way, or if you preferred, you could have a circle here, right? Now putting a circle up here is going to give us a more tricky equation of a circle. It works just fine, it'll just be a little trickier. In fact, maybe after we do this problem, we'll get it set up for if we had put the circle up here. All right, so this thing is half full, so basically this bottom half is all full of milk, right? The bottom half is all milk in here. So maybe just kind of draw so that this is all milk here. And we want to figure out the force against this side of this. So we can do what we did in the last one. I'm going to basically just draw in a little sample slice here, a little sample section of this, a little rectangular piece. And then I'm just going to find the force against this sample strip. I'm going to find the force against this strip and then integrate wherever these strips are. All right, so I'm going to do the same thing that we did before. We will find the force against the sample strip. So to start off, we start off with finding the area of the strip. So the area of the sample strip is going to be the same as last time, right? So if I know this x-coordinate right here, if I know the x-coordinate, then this length is just 2 times x, right? 2 times x, and the height would be dy. So just like before, this is going to be 2x dy. And then, so that's the area. So then to find the pressure against this sample strip, well, pressure equals weight density times depth. This is a formula we use again. We use quite a bit. So, okay, weight density. Well, this is milk. So if you look on the first page of the handout, milk, the weight density of milk is 64.5 pounds per cubic foot. And then the height. Now this is where I want to think of it still as height minus y, because it makes this kind easy. If I think of height minus y, I get 0 minus y, because the height of this water, the way we have it set up, the height is right at 0, right? We go minus y. And the reason it will work is because if we're at this point right here, we have this point, well, this y is going to be a negative value. So when we go 0 minus y, we end up with minus minus. So we get a positive value here. So once again, for this, I'm just going to always go height minus y. Height, depending on how you set this up. The way it's set up here, the height of the water is right at 0, right? Because it's half full. So we go 0 minus y, and that'll give us the height of the water. Okay, so that gives us the pressure. Otherwise, if you just think about it, all these y values are negative, and we have to have this be the height, so it'll be a positive value. So you just go minus y. That'll give you a positive. But it's much easier just to always think this depth of the water, we can just go height minus y. Then the next thing we need to find is the force against the sample strip. And that is just going to be force equals pressure times area. Okay, so the force is going to be 64.5 times minus y, just going to get rid of the 0, times 2x dy. So then we can find the total force. This is going to be, let's see, 2 times 64.5. I'll pull the constants out front. I'm going to pull the negative out there too, and then we'll get x, y, dy. And now y, the way we have this set up, y is going to go wherever the strips are, right, from -3 up to 0. -3 to 0. And then we need to figure out what to do with this x, right? It's a dy problem. We need to get rid of this x. So we'll go back to this. So if I look at this, this is an equation of a circle centered at the origin with radius 3. This is going to be x squared plus y squared equals 9, right? So then we need to solve this for x. Well, if I have x squared plus y squared equals 9, that means x squared equals 9 minus y squared, which means x equals the square root of 9 minus y squared. And I'm going to use the positive one only, not the negative, because these are these distances here for x, which are going to be positive distances. So we can put this in place, and this will give us -2 times 64.5 from -3 to 0 of y times the square root of 9 minus y squared dy. And this one is pretty simple u substitution. So if we go ahead and do a u substitution here, you will end up getting 1161. And what's the unit of measure here? We're using feet, so it's the English U.S. customary system. So for force, it's going to be pounds. Okay, so I don't want to take the time to go through this because I'm sure we know how to do this. This is just a regular U substitution. Now, one thing that you will notice, so if you happen to check this on the TI-83 or 84, it makes a small error. The Cordic algorithm, I think it just times out a little too quickly, and you get something like 1161.000046. So this is the actual answer. And if you go ahead and do a quick U substitution here, you'll end up getting this answer. Okay, but mainly what I want to concentrate is how to set these up. Usually once they're set up, they're not too bad. There are some exceptions, but for the most part, it's the setup that gives us the most work. But also, I wanted to show you what if we had set this up a little differently, just so we can make sure we're really solid on how this works. I could have just as easily set up this problem by putting the circle up here. Now this is a more complicated circle, but if you remember the formula, x minus h squared plus y minus k squared equals r squared. This is the equation for a circle centered at hk. So this is centered at 0, 3. So if you were to do this, the equation becomes x squared plus y minus 3 squared equals 9. So it's a little more complicated. So at this stage here, when we solve this for x, we get a little bit more complicated integral. So it's definitely, this way is going to be way, pretty much, it'll be quite a bit harder to do by hand, but it still works. So if we set it up this way, and we could think about it, okay, this is half full, so it goes to this point, it's half full. So we could set our sample strip up right here. Now, of course, with this goes up to 6, right? It goes up to 6 here. So when we set up our sample strip, I'll go through the same process here. So we have the area. The area is still going to be 2x dy. Pressure. That's going to be, well, I'll do the same thing. Pressure equals weight density times depth. Weight density 64.5. Depth now, think about where this is at. This is at 3, right? So this is a 3 right here. So that's 3. So now the depth is going to be, if this is y, the depth is going to be 3 minus y, right? So if this is y right here, this distance would be 3 minus y. Let me just write it in here. If this is y, this is going to be 3 minus y because it's half full. So it's going to be 3 minus y. And then the force is pressure times area. So that is going to be 64.5 times 3 minus y times 2x dy. So when you set up this for the total force, we're going to get 64.5 multiplied by 2. I'll bring those out front. Then we're going to have, let's see, x times 3 minus y dy. Now here we're going to integrate from 0 to 3, right? We'll go from 0 to 3 here. Go from 0 to 3. And then we're going to have to figure out what x is. So I need to solve this for x. So in solving this for x, I would subtract this from each side and get 9 minus this. And then I have to take the square root. So once you do that, you're going to get 2 times 64.5 times the integral from 0 to 3. And now our x is going to be 9 minus y minus 3 squared under the radical times 3 minus y dy. Now to actually solve this one, we have to distribute this through here, and we end up with 2 integrals to solve. And it's going to be definitely more work. Now if you punch this in the calculator, you get exactly the same answer. The calculator makes the same little error, gives you 1161.000046. If you do it by hand, it will take some time, but you'll get the correct answer, which is this. So a couple different setups. This one definitely is the easier way to go, but they both work. You could literally put this circle anywhere you want to, but if you don't put it in one of these two, it could get really messy. But in theory, you can put it anywhere you want. So, okay, that is how to take care of example number 2. So you got one more to try here, and I think you should be pretty good to go on these. This example is actually one from our book. It's in the 8th edition and the 9th edition of Stewart. It's example 1 in the book. It's on page 558 of the 8th edition and page 577 on the 9th edition. And I just wanted to mention that because the book uses a little bit different technique. It uses similar triangles. But I'm going to use the same technique we used in chapter 6, and we use in all of these, just so you have one technique. And sometimes it's just easier. If you have one technique that works on everything, I typically would just teach that technique. So let's take a look at this one. So we've got a dam in the shape of a trapezoid with a height of 20 meters. The width is 50 meters at the top and 30 meters at the bottom. You want to find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So this one, we definitely need a picture. All right, so here's a picture I came up with. So it said it's 30 meters at the bottom. So go negative 15, 15. So I can center it right at the origin here. And then it's got a height of 20 meters. So this is 20 meters up. The width is 50 meters at the top. So since it's centered, we go out 25 meters. And this is 20 meters up. And then it said the water level is 4 meters from the top of the dam. So here's the water level. Okay, so once you got this picture, everything else is the same. I'm just going to think of a little section here, or a little strip of the dam. And I'm just going to find the force against that sample strip. So I'll do it in pieces again. So we'll do the area of the sample strip, which in this case, once again, if I know this point right here, I would know this x coordinate. So the length of that rectangle would just be 2x. And the little thickness there, the height of it would be dy. Now this 2x dy is pretty common, but it's not always the case. So sometimes we might have something like this. Maybe we'll have some rectangular piece that looks like this. And maybe the water level is here. Well then, if this is a rectangular piece and we have this little sample strip, well then this distance is just going to be x, not 2x. We keep getting 2x because of the symmetry we have, but we won't always have that. So just kind of be aware, it's not automatic. If we have a picture like this, this is going to be x dy. Okay, so just wanted to just throw that out there, make sure everybody's okay with that. All right, so we got the area is 2x dy. Then we need to find the pressure. So the pressure against the strip, right? Pressure against the strip. Well, pressure equals weight density times depth. So that is going to be, in this case, it's the metric system, so it's 9,800. The depth is always going to be height minus y, the height of the water. Well, the height of this water is 16 meters, right? Because it's the water level is 4 meters from the top of the dam. We know the top of the dam is 20 meters. So the height here is going to be 16 minus y. And it makes sense even if you just look at the picture here. This right here is y. And we know this whole thing is 16. So that means that this distance has to be 16 minus y. Right? But the easiest way is just always remember this is height minus y. So that gives us the pressure and then the force against the strip. Force against the strip, force equals pressure times area. So the pressure is 9,800 times 16 minus y times the area, which is 2x dy. So that gives us the force. And once we have this, we can find the total force against that dam by integrating all these little sample strips. So that is going to be, once again, I'll pull the constants out front. So we get 9,800 times 2 times x times 16 minus y dy. We're going to integrate wherever the strips are going to be. So from here, from this picture, go from 0 to 16. And then, as usual, we just have one more last piece. We need to figure out what x is in terms of y. Well, we can do that because we know we've got a couple of points on this line. And if we just have one line, that'll give us a relationship between x and y. So we need to be able to find the equation of a line through this point and this point. So if you think to the glory days of high school algebra, when you first learned how to do this, let's do this off to the side here. Let's just go, okay, the slope of that line, y2 minus y1 is 20 minus 0. x2 minus x1 is 25 minus 15. Again, we're just using the old slope formula, y2 minus y1 over x2 minus x1, which you probably have stuck in your brain for the rest of your life because you've seen it so many times. So we do it on this point and this point. And that will give us a slope of 20 over 10, which is just 2. So the slope is 2. All right, let's make some room here. Get rid of this thing. And then we need to go, we use this y equals mx plus b. I'm going to plug in the slope here. And I'm gonna plug in the point 15, 0. Again, it doesn't matter which point you pick, but I'm going to pick this one because it has a 0. So plug that in for x, that in for y. So then we'll get 0 equals 2 times 15 plus b. 0 equals 30 plus b, which means that b equals negative 30, which means the equation of our line is y equals 2x minus 30. Now, we really need x in terms of y. This is y in terms of x. So I just have to solve this for x. So if we solve it for x, if I add 30, we get y plus 30 equals 2x. Divide everything by 2, and we'll get x equals y plus 30 over 2. So this is what I will plug in for the x up there. So what will happen is this 2 here will cancel that 2, right? So I'm going to replace this x with y plus 30, and I'm going to just get rid of that 2. Okay, so that will give us 9,800 times y plus 30 times 16 minus y dy from 0 to 16. Okay, so now we have to integrate this one. What are you thinking? Which technique? Trig substitution? No, not that. That would be fun. I know everybody enjoyed that section 7.3, but this is actually not too bad, right? Just have to do a little algebra. Remember the FOIL method? So let's do a little algebra on this and see what we get. 9,800, 0 to 16. First times first gives us 16y. Outside times outside minus y squared. Inside times inside plus 480. And then last times last is minus 30y. dy. And we can definitely clean this up. So this would give us 9,800, 0 to 16, minus y squared, minus 14y plus 480 dy. Right, and then from here, it's not too bad. We just have a power rule, right? This integral is not bad at all. 9,800 negative 1/3 y cubed minus, let's see, 7y squared plus 480y from 0 to 16. So let's do another step here. We can see the 0 is not going to really do anything for us, but we will get 9,800 negative 1/3 times 16 cubed minus 7 times 16 squared plus 480 times 16 minus what we get when we plug in the 0, but the 0 will have no effect on it. And then if you go through the calculations here, type it in your calculator, you'll get a pretty decent sized number, but roughly I'm going to write in scientific notation 4.43 times 10 to the 7 newtons. And remember, you can put the full number here if you want to. Remember, in this class, we don't talk about significant digits. It's just not something that we cover in Calc 2. So you'll take care of significant digits or significant figures in your chemistry and physics classes. So we don't cover it here. So we're a little bit sloppy in that department just because we don't officially cover it. So you can write it like this. You can put the number you get from your calculator. It's all fine. The thing to remember though is this: the units here are newtons, right? Because this is the metric system. So okay, I think that should give you what you need. Just think of those formulas in the 3 boxes, and then the technique that we've used in these problems should get you what you need. So so try 8.3. The first part, right? We'll take care of the second part with center of mass next time. But try them out and let me know if you have any problems. And I will talk to everybody soon.